Good morning, everyone. Welcome to Introduction to Electronics and Communication subject. Myself, Darshan B, Assistant Professor, Department of ECE, SJBIT. So today we are going to discuss some topics from Module 1 on Introduction to Electronics and Communication. So today we are going to discuss on amplifiers. Amplifier is a circuit which converts weak signal to strong signal to increase the amplitude of the signal. It's considered type of amplifiers. So here DC coupled amplifier, large signal amplifier, then small signal amplifier. So like that we are going to categorize. First, AC coupled amplifier. In AC coupled amplifiers, stages are coupled together in which that the DC levels are isolated and only the AC components of the signals are transferred from stage to stage. So in the DC coupled amplifier, DC and direct coupled amplifier, stages are coupled together in such a way that the stages are not isolated to DC potentials. Both AC and DC signals components are transferred from stage to stage. Next, large signal amplifiers. Large signal amplifiers are designed to cater from appreciable voltage and current levels, typically from 1 volts to 100 volts or more. Small signal amplifiers are designed to cater for low level signals, normally less than 1 volts and often much smaller. Small signal amplifiers have to be specially designed to combat the effect of noise. Next, so the audio frequency amplifiers. Audio frequency amplifiers operate in the band of frequency that is normally associated with audio signals, that is from 20 Hz to 20 kilohertz. This is so the audio signals or audio frequency amplifier. Wideband amplifiers are capable of amplifying a very wide range of frequencies, typically from a few hertz to several megahertz. Radio frequency amplifier operates in the band of frequency that is normally associated with the radio signals. This example is the frequency range is from 100 kilohertz to 1 gigahertz. Low noise amplifiers are designed so such a way that they contribute negligible noise to the signal being amplified. These amplifiers are usually designed for use with very small signal levels, so that is less than 10 millivolts. So consider gain. So what is gain? So here we are going to consider the different types of gain: voltage gain, current gain, and the power gain. So gain is normally a output by input. Either it may be a voltage, or current, or power. Consider the voltage, the gain, or current gain, or power gain. Before that, you consider the block diagram of an amplifier showing input and output voltage and current. So in this amplifier, we are considering input voltage is Vin, input current is In, output voltage is Vout, output current is Iout. Input and output. The gain is output by input. The voltage gain is denoted as AB, that is output voltage to input voltage, Vout by VB. Current gain is nothing but AI, is output current by input current. Power gain is denoted as AP, is ratio of power output divided by power in. Since the power is the product of current and voltage P is equal to V into I, so that we can write the power gain EP is P out by P in, so that P out is I out into V out, so P in is I in into V in, so that we can write I out by I in into V out by V in, so that AP, this power gain, is equal to current gain into voltage gain. Considering example using a voltage gain and current gain and power gain. So an amplifier produces an output voltage of 2 volt for an input voltage of 50 millivolt. The input and output currents in this condition are respectively 4 milliampere and 200 milliampere. So in this case we have to find out the voltage gain, current gain and power gain. So this is, we already know that in the last slide we have discussed that what is voltage gain, current gain and power gain. AV is output by input voltage, V out by V in, so V out is 2 volts, they are already given. So V in is 50 millivolt, so that EV, voltage gain, is 40. The second parameter we need to consider is the current gain. The current gain is calculated, so using AI is I out by I in. I out is, the current output is 20 milliampere, input is 4 milliampere, so that the current gain is 50. The power gain you can calculate in the two methods, the power output and the power input. You can find out the power output, power input, and we can substitute them. Otherwise, we know already that the power gain is the multiplication of voltage gain into current. Using that, you can write that voltage gain and current gain is already calculated, so that we can write 50 into 40 is equal to 2000. The input and output resistances. So you can see that in the figure, the amplifier. So you're having input and output. So you're having some input and output resistances there. The input resistance is the ratio of input voltage to input current, and this is expressed in the ohms. The input of an amplifier is normally purely resistive. You can consider the resistance. You already know that according to Ohm's law, R is equal to V by I. Okay, in that case, voltage, input voltage divided by input current. So in some cases, the reactance of the input may become appreciable. So in such cases, we would refer the input impedance rather than input resistance. Means when you are going to consider only resistance part, means you can write the input resistance. When you are going to consider the reactance parts come into picture, so in that time, instead of resistance, we can call it as impedance. Output resistance is the ratio of output circuit output voltage to the output current. Okay, in the time, so in which way we are going to take the output voltage and output current? Okay, that is the ratio of open circuit output voltage to the short circuit output current, and it is measured in ohms. So input resistance and output of an amplifier is normally a pure resistive. In case if it is having the reactance parts coming picture in the output, so that we can call it as output impedance rather than output resistance. So consider the frequency response and bandwidth. Okay, so consider the frequency response characteristics for various type of amplifiers. So observed in the figure. So for this response curves of this type, frequency is almost inversely plotted on a logarithmic scale. The frequency response of an amplifier is usually specified in terms of upper and lower cutoff frequencies of an amplifier. These frequencies are those at which the output power has dropped to 50%. Okay, so we can consider, otherwise you know that we have to take the minus 3 dB point, or where the voltage gain has dropped to 70% and it is mid band values. We can observe the frequency response of the bandwidth output power plotted against the frequency. You can consider consider output voltage plotted against the frequency. These are the two the curves we are going to show that. So F1 and F2 frequency we are going to get. So using that we are going to find out the bandwidth. So this is the example. So how mid voltage gain and upper and lower cutoff frequencies of amplifier, whose frequency response we are going to show them. We can observe, we can find out using F1 and F2 frequency, and we can find out the bandwidth also. Bandwidth. The bandwidth of an amplifier is usually taken as a difference between the upper and lower cutoff frequencies F2 minus F1. You can observe from the figure. Bandwidth of an amplifier must be sufficient to accommodate the range of frequencies present within the signals that is to be presented with. Many signals contains harmonic component. To reproduce a square wave, for example, requires an amplifier with a very wide bandwidth. Phase shift. What is phase shift? Phase shift is the phase angle between the input and output signal voltages measured in degrees. The measurement is usually carried out in the mid-band, where for most amplifiers the phase shift remains relatively constant. Note all that the conventional single stage transistor amplifiers provide phase shift of either 180 degree or 360 degree. So consider negative feedback. So negative feedback amplifier. So in the negative feedback amplifier, we are considering the amplifier gain is AV and phase shift is 180 degree. The amplifier gives the 180 degree phase shift. So we are going to consider input is Vin. This is amplifier input. So we are going to take the negative feedback. Negative, so because the amplifier gives 180 degree phase shift, we are going to get minus and plus. So that negative feedback we are going to apply feedback network. Feedback ratio is beta. Feedback phase shift is 180 degree. So feedback network is also give 180 degree phase shift. So plus and minus we are going to apply here. So it's minus and plus we are going to get. So this is minus and plus minus minus. We are going to subtract the voltage feedback to the input side. That is beta V out. So new amplifier input is V in dash is V in minus beta V out. The input of the feedback network is V out. So output of the feedback network is beta V out. Beta is the feedback ratio. Many practical amplifiers use negative feedback in order to precisely control the gain, reduce distortion and improve bandwidth. The amount of feedback determines the overall gain. You can consider because of this the form feedback has the effect of reducing the overall gain of the circuit. This form of feedback is known as negative feedback. Here alternative form of feedback where the output is fed back in such a way that input is such a way that reinforce or rather than to subtract from it. So this is called positive feedback. This form of feedback is used in the oscillator circuit. The amplifier circuit use the negative feedback. Of an oscillator circuit we are going to use positive feedback. So we are going to consider that so we are observed that with the figure the overall gain G is V out by V in. So we can observe that V in is the amplifier input, V in dash, V in is the normal input to the system, V in minus beta V out, because we are considering the negative feedback, so that we are going to subtract the feedback ratio from the input. So by applying the Kirchhoff laws we are going to get, so we can consider V in is V in dash plus beta V out. And V out is AV into V in. Okay, AV is the internal gain of the amplifier. Overall gain G is V out by V in. So what is V out? V out is AV into V in dash divided by the V in is V in dash plus beta V out. So that we can substitute that the V out is AV into V in dash. So then So we are going to take the V in dash common. We are going to get AV divided by 1 plus beta AV. So V in mean will get cancelled. So finally we are going to get, so G is equal to AV divided by 1 plus beta AV. So here when you are going to consider the AV is very less, or you can consider AV is very large. AV is very less means AV divided by 1 plus beta AV. This is the one will be dominating. And when you are going to consider AV is more value, we can neglect that one, so that we are considering AV divided by the beta AV. So AV will get cancelled. G is equal to 1 by beta. AV is very large. This is the example. So considering that, so when you are going to consider voltage gain is 50, so feedback ratio is beta is 0.1. so when you are going to substitute this in this formula, G is equal to AV divided by 1 plus beta AV, you are going to get, so gain, overall gain is 8.33. This is another example. If you are going to consider the overall gain, they mentioned that the overall gain is also, overall gain is 20, voltage gain is 100, B feedback ratio need to find out. So feedback ratio is 0.0. So in order to provide a sufficiently large value of gain, it is frequently necessary to use number of interconnected stages within an amplifier. So consider the overall gain of an amplifier with the several stages, that is a multi-stage amplifier, is simply the product of individual voltage the gain. You can consider so many the stages. If we are going to use the individual stage voltage gain AV1 into AV2 into AV3, we have to multiply all these voltage gain to get the overall voltage the gain. Increase in gain can only be achieved at the expense of a reduction in the bandwidth. The consider multi-stage amplifier. A multi-stage amplifier is nothing but, so these different the stages of amplifier we are going to use instead of a single stage amplifier. Okay, in this we have to consider that, so different methods used for interstage coupling. How to couple that one stage to another stage. Signals can be coupled between the individual stage of a multi-stage amplifier using one of the number of different methods we are going to observe it. You can observe here, so typical RC coupling between the stages. RC we are going to use to couple this, the first stage to second stage. We are going to use LC coupling circuit, L and C component. We are going to use transformer coupling and then direct coupling. Consider the most commonly used method is RC coupling. So it's shown in this figure. In this coupling method, the stages are coupled together using capacitor having a low reactance at the signal's frequency and resistance. So here we are considering the resistance and capacitance are the coupling element. So in the second one, so we are going to use typical RC coupling between the stages. RC coupling between the stages, a similar coupling method known as L and C coupling. In this method, the inductors have a high reactance at the single signal frequency. RC components we are going to use between the two stages. LC components we are going to use between the two stages. Then the third one is the transformer coupling. So we are going to consider transformer between the two stages. Fourth stage is direct coupling. Output of the first stage is directly applied to the second stage. So consider positive feedback. Positive feedback we are going to use in the oscillator. The alternative form of feedback where the output is fed back in such a way that as to reinforce the input is known as positive feedback. So we are considering that the block diagram of amplifier stage with positive feedback applied. So phase shift is 180 degree. and the feedback network provides the another 180-degree phase shift. So from this the overall gain is V out by V in, applying the Kirchhoff law. So V in dash is V in plus beta V out. So that V in is equal to V in dash minus beta V out. So that V out is AV into V in. Overall gain we are going to consider, when you are going to consider here, we are going to subtract instead of addition. Okay, so here this is the exact opposite of negative feedback. Overall gain G is AV divided by AV into V in divided by V in dash minus beta V out. So that we are going to take the V in dash common, so that will get cancelled. So that the overall gain is AV divided by 1 minus beta AV. Thank you.